Hi everyone. Today we continue talking about the production of materials, and our second topic is called the production of ethylene and petroleum fractions. Now ethylene is the same thing as ethene. It has a chemical formula of C2H4 and its chemical structure looks like this, with a double bond between the two carbon atoms. Now ethene and ethylene are the same thing, so don't get confused, and I'll tell you why in a little while. So let's start by looking at this picture. This is something called a catalytic cracker, which we'll be talking about shortly. And what happens is crude oil and various fractions go into the catalytic cracker and we come out with ethene or ethylene. Now I'm going to write up here C2H4. That's our target compound, which is what we want to produce, and I'll tell you why as we go along. So looking at the uses of petroleum fractions, if you remember back to last lesson, I discussed a fractionating column or fractional distillation, where we put crude oil in and we get different fractions out at different boiling points. If you remember, the lower boiling points were at the top of the column, BP for boiling point, and the higher boiling points came out lower down the column. So the larger the molecule comes out at a higher boiling point, and the lower ones at the top, the shorter ones. Now, I'll just rub that out of the way for you so you can see. The lighter fractions, the ones up the top, are used in fuels such as petrol and LPG, and also in petrochemical manufacture, such as these products here, plastics, solvents, adhesives, all sorts of things that you see around you every single day. The heavier fractions that come out of the column down here, they're also used in fuels, but also for lubrication applications and many other things. An example of a heavier fraction would be kerosene. So now let's look at the composition of typical Australian crude oil. Now the majority is petrol, there's some diesel, some kerosene. But what I want you to take from this diagram is that there's many different things in crude oil, and unfortunately, the shorter chain hydrocarbons, there aren't too many of them. We get lots and lots of longer chain hydrocarbons, but not too many shorter chains. So what we need to do to get shorter chains, or our target compound, ethylene, is to crack these longer chains into shorter chains. So if you imagine this as a long chain hydrocarbon, for example with 10 carbon atoms, if we crack it like that, for example, and we can turn it into shorter chains. So a good analogy of that would be to think of an egg. If you had the whole egg, it would be one large eggshell. If you crack it, it goes into many, many smaller parts of eggshell, and that's what we're doing here. So when you hear the word cracking, which is important to remember for this part of the topic, think of longer or bigger going into shorter, okay? So, alkanes. Now they're useful as fuel, like this one, which is propane, but unfortunately they're not very reactive because they're saturated, which means saturated compounds mean that the carbon atoms are bound to all the hydrogen atoms. There are no other places that it can bind to any hydrogen atoms. There are no bonds that can be broken, and that's what we call saturated. So if you think of your polyunsaturated margarine, for example, unsaturated, saturated, unsaturated. People are thinking, do we eat butter? Do we eat margarine? What's saturated? What's unsaturated? Now you can tell your friends, saturated means that it's all single bonds. So therefore, unsaturated means that there's either a double or a triple bond. So alkenes are unsaturated molecules, which means that this bond, this double bond, can be broken and other atoms can come along and bind here. So therefore, these alkenes are more reactive than alkanes. And if you think about it, we'll talk about alkynes eventually, but if you think about reactivity, an alkene is more reactive than an alkane, and similarly, an alkyne with a triple bond is more reactive than an alkene. But we'll go into that in a different topic area. So just rub that out. So, because of the double bond of the alkenes are more reactive, It's ideal for the synthesis of petrochemicals because we can break that bond by various synthetic procedures and add on different atoms, thus creating completely different molecules for different uses. So, what we're talking about today is the production of ethylene. Now this is ethylene here, C2H4, our target molecule. It's versatile and widely used in the petrochemical industry, and it's the raw material for production of plastics and industrial chemicals, such as paints and solvents. Now, the proportion of ethene found naturally in petroleum unfortunately is very small, but we as humans have a very high demand for ethylene. So because we can only get so much out of petroleum, we've found new and inventive ways to get more ethene out of petroleum. So for example, if this is petroleum, this is a barrel of petroleum, we might only get that much ethene, for example. We need more than that. Maybe our demand is this much. That's how much ethene we need. So what we do is we use the leftover parts to produce ethene. And that's, how do we do that? That's what we're about to discover. Now I did mention cracking, and that's how we get more ethene. So we crack longer chain fractions into the smaller chain fractions. That's catalytic cracking. There's two types of cracking, catalytic cracking and thermal cracking, and you'll need to remember this. Let's start by looking at catalytic cracking. We start with a long chain hydrocarbon, for example, 1 meth, eth, prop, bute, pent, hex, hept, oct, non. Let's say nonane, 9 carbons. Crack it down and we'll get our target molecule and a byproduct, which we'll discuss later. But just imagine a longer molecule going into shorter molecules. Now, when we do this, we put it in the catalytic cracker, if you remember that picture of the catalytic cracker. And the longer chains that go in, we call feedstocks, okay? You'll need to remember that term as well. That's an important word to remember. So here's our catalytic cracker. Our feedstocks go into this cracker, and what comes out is ethylene. So let's imagine that this is our reaction vessel, okay? This is a very large reaction vessel nonetheless. So in go the long chain hydrocarbons, whatever length they may be. Now they could be different lengths, and we'll get to that. And out comes C2H4. I'll just move that over so you can see. Excuse me for a moment. I'll put it just over here. Okay, so our long chains go into the reaction vessel, and out come our target and a byproduct, or many byproducts, depending on the reaction. But what we need for this to go forward is a catalyst. Otherwise the reaction is very, very slow and the activation energy is very, very high. So we use a catalyst, and they're called zeolites, which is an aluminosilicate. Now, from the name aluminosilicate, you can probably think aluminium. Yes? Amino, oxygen, and silicate, silicon. So they're inorganic molecules made of aluminium, oxygen, and silicon. The temperature in this vessel is around about 500 degrees Celsius, which is pretty high, and the pressure is just above atmospheric. Now, atmospheric pressure is approximately 101.3 kilopascals. So in there it would be around about 105, 110. So looking at an example now, what we take is a longer alkane and we get a shorter alkane and an alkene. In this case, of course, our target compound, ethylene. So here it shows you decane, 10 carbons means dec, the prefix dec. Going to C8, H18, another alkane. Now there's 8 carbons, so the prefix is oct, octane, and ethylene. Now, looking at zeolite, our catalyst, this is quite important. As I said, it's an inorganic crystal, and if we imagine our reaction vessel again, we've got our longer chains coming into the reaction vessel. So in they go, And here is our zeolite catalyst, a very large drawing of a zeolite catalyst. And on the outside of the zeolite catalyst, or the crystal, it has pores. Now these pores are able to adsorb, with a D, adsorb, the reaction molecules. So what happens is, I'll just tell you, adsorb, I was going to describe to you, means, as opposed to absorb when something is going in, adsorb means just stick to or cling to. So it's just clinging to the surface of this crystal. So for example, it comes in and just sticks to it. And by doing so, if you imagine one of these long hydrocarbons sticking to one of the pores, the aluminosilicate, the chemical reaction that's going on there, will actually weaken the bonds of these long hydrocarbons. And by weakening them, they'll split up and you'll get shorter chains coming off. So there you'll get your ethylene and your byproduct, your other alkane. Okay, so that's what an aluminosilicate does. And we need that catalyst. It speeds up the reaction. It increases the yield of our product. And aluminosilicates can be specifically synthesized in laboratories so that it will have specific pore sizes depending on the length of the hydrocarbon chain. So if you think back to, this is a very simplistic way to think, but it's a good way to remember. If you think back to when you were little and you had a block set and you had to put the right blocks in the right holes, and only the triangle block would fit in the triangle hole and the circle into the circle, etc. An aluminosilicate is pretty much like that. We can make pore sizes either small or bigger or medium. They'll all be the same, but we can make them how we want them for the specific chain length of that hydrocarbon, which is great. So we can control the products that are formed by whichever hydrocarbon we have. C10, we'll make holes the right size. That's a C10, that's the right size for that. We'll use that zeolite for this particular reaction. So now on to the other type of cracking. We've just looked at catalytic cracking. Now the other type is steam cracking. In steam cracking, they don't use a catalyst. They use very, very high temperature conditions, which is costly because to get the temperature up higher, you need to put more energy in. So that's more costly. And unfortunately, with steam cracking, it's difficult to control the end products. So catalytic cracking, it seems to be more specific. What happens in steam cracking is that you start with an alkane, and usually a relatively short alkane, and you end up with a small alkene, our end product, and a byproduct. In the case of ethane, our byproduct is hydrogen. So, a mixture of the gaseous alkane is introduced, and steam is passed through a hot metal tube. And as they go down the tube, at a very high temperature, 750 to 900 degrees, so it's higher than catalytic cracking. The pressure is about the same, 101 point, just above atmospheric, and you'll get your end product, which is ethylene. So here I'm going to give you two examples. This one we've shown for you, which is ethane. So if we start with ethane and we go through the steam cracking process, which is this metal tube that I described, we get ethylene, and our byproduct is hydrogen gas. Now with all byproducts, as I spoke about before, with all reactions there's a byproduct. With all byproducts, they can either use the hydrogen gas for another purpose, or they dispose, in industry they dispose of it in whatever way they choose. So what we start with is ethane. Going through the steam cracking process, we get ethylene and hydrogen gas. Now for propane, which is 3 carbons, meth, eth, prop. Now just think about, while I'm drawing this, what do you think the byproduct will be? We know the end product is going to be ethylene, because that's what we're doing. We're steam cracking. I'll just say SC for steam cracking. We know we're going to get ethylene, C2H4, this one. What's our end product? So let's look at both sides of the equation. Now think about conservation of energy, which is the basis of all our chemistry, which means you cannot create or destroy matter. So let's start by counting carbons on the left and the right, see what we're left over with. On the left we've got 3 carbons, on the right there's only 2, so our product must have 1 carbon. Now count the hydrogens. Whoops. 1, 2, 3, 4, 5, 6, 7, 8. 8 on the left, 4 on the right. 8 minus 4, you've got 4 left. What's that? Methane. Okay? So that's the byproduct of steam cracking propane. So our two main compounds that we steam crack are either ethane or propane. They both produce ethylene and a byproduct, whether it be hydrogen or methane. So that's the end of our theory for now. So what I want you to remember, and what I've discussed today, are the ways in which we can produce ethylene. And why we do that is because ethylene is needed in the petrochemical industry for so many different applications, which we'll talk about in our next topic, which will be the applications and the reactions of ethylene. But today we're talking about the uses and, how we actually extract ethylene and synthesize ethylene. Because when we get our crude oil and our petroleum, there's very little ethene, but we need ethene, and that's because it's more reactive than alkanes, and we can use it because of its double bond. So let's now look at some questions, and we'll start with question 6. What is the difference between a saturated compound and an unsaturated compound? Okay, if you remember, I told you that a saturated compound has carbon atoms with only single bonds. So no bond can be broken here with another hydrogen coming along. So you cannot put any more hydrogen atoms on that molecule. So let's name it while we're here. Meth, eth, pro, but, pent. So that's pentane. So all alkanes are saturated compounds. So similarly, an unsaturated compound is a compound that has at least one or more double or triple bonds, which means that the double bond can be broken and a new atom can come along and bind to it, whether it be hydrogen or something else. Now don't be scared by this X. X just means it could be any other atom. X just means it's not hydrogen. X means any other atom. So, because these double or triple bonds are so reactive, they can be broken and other atoms can come along and bind to them. For example, which we'll look at in the next topic, we can break this bond and we can bring along a bromine atom, for example, and that can go in there and become the X, and then we would have bromine atoms there that weren't there before. And the great thing about this is that by putting bromine atoms there, that is a completely different molecule than pentane, which we have here, and it has different properties and different uses. So that's why double and triple bonds are so important for the petrochemical industry, because when they break them, they put a new element in there, and you have a different compound, which we can use for all sorts of different things. So now let's look at question 7. Provide IUPAC names for the following. Now, IUPAC stands for the International Union of Pure and Applied Chemistry, and it's the way that we name all chemical compounds all around the world. So, let's start with part A. When we're naming carbon compounds, we always start by counting the number of carbon atoms, and that will be the first thing we look at. So, the prefix will always be the number of carbon atoms. So, meth, eth, pro, but, pent. So, this will start with pent. That's the first thing we do. And then we look at the suffix. The suffix is whether it's an alkane, an alkene, or an alkyne. And that's to do with the bonding. So because it has all single bonds, it's an alkane. So our suffix will be ane, pentane. So that's part A. Let's look at the second one. Again, start with the prefix. How many carbons? Meth, eth, pro, but, pent, hex. So our prefix is hex. Let's look at our suffix. Now, we have a double bond, so it's an alkene. So our ending is going to be ene. But it doesn't end here. With alkenes and alkynes, you have to look at where the double or triple bond is, because that's important for what goes at the start of this molecule. The name of the molecule. So this will be part 3 for double and triple bonds only. So now what we do is we count in between the carbon-carbon bonds. So this bond, we'll name 1. We always go from left to right and we name the bonds. We number them. 3, 4, 5. You don't name them between carbon and hydrogens, only between carbon and carbon. So where's our double bond? It's at number 3. So we put a 3 in front. So this is 3-hexene. Okay. So the final one, part C, start with the carbons, meth, eth, prop. So prop. What's our ending? Double bond, alkene, propene. Now, we always have to look and count the carbons. 1, 2. But the thing is, because this molecule can be flipped over and it will look the same, if, for example, you were looking from the other side of the blackboard this way, you would see that it's exactly the same both sides. So you don't need the numbers. It reads backwards and forwards the same way. So this will just be propene. So while I'm here, I'll give you one more example and see if we can name this. Okay, 1. Okay, let's try this. Right, as always, start with the start with the carbons. Meth, eth, prop, but, pent, hex, heps. So it's heps. Look at the ending, double bond, ene. Count the carbon bonds. 1, 2, 3, 4, 5, and 6. So this molecule here will be 4 dash, don't forget the dash, that's very important, 4-heptene. Okay, so we'll move on to our next question now. Question 8. The following equation represents a process used in the production of ethylene from petroleum fractions. What is the name of this process? Well, as we've been discussing throughout this topic, we're producing ethylene. There's a catalyst. So you've got to start thinking cracking? Yeah, it's catalytic cracking. So what's happening is we have a long chain molecule, in this case C8, octane, going to ethylene and ethane, excuse me. So again, longer chains broken down into shorter chains is catalytic cracking. So if you see catalyst, always think catalytic cracking. That will help you in answering these kind of questions. So that's our answer. Question 9. The following chemical reaction occurs during the cracking of hydrocarbon molecules. C18 going to 2C8s plus Z. What is the name of Z? Well, I touched on this a bit earlier, so let's go through it. We start with C18. So when you see a question like this and you have a Z and you have to figure out what is this compound, what you do, think about conservation of energy. Same number of atoms on the left should be the same number of atoms on the right. So I always start by going, how many carbon atoms are on the left? There's 18. How many hydrogen atoms are on the left? 36. Goes to, how many carbon atoms on the right? Don't be confused. Never forget the 2 in front of a molecule. There's 16 carbons here. So always keep thinking when you see questions, 2 times 8, 16 carbons. 2 times 16, 32 hydrogens. Okay, don't forget that. That's very, very important. Plus Z. So how many carbon atoms are left over that will be here? So let's just write, actually put that just below so you can see how many carbon atoms are below the Z, how many hydrogen atoms for the Z. 18 minus 16, so there's 2 of those. How many hydrogens left? 36 minus 32, 4. C2, H4, ethylene. So there's our equation that balances out, and the answer, of course, is ethene or ethylene. So when you get a question like this and you see a Z, think that's great. Always balance out your carbons on the left and the right, balance out your hydrogens, whatever left, sorry about that, I forgot the hydrogens, 4 even, forgot to write that in. Yeah, always think what's on the left, what's on the right, whatever's left over, that's your mystery target compound. And finally for today, question 10, describe the process of catalytic cracking. Now you should be experts by now at this one. So it's a chemical process. It uses a catalyst called zeolites, which is an aluminosilicate, to cut down longer chain hydrocarbons into shorter chain hydrocarbons. And if you remember, our aluminosilicate with its pores of specific size will take on these large hydrocarbons and break them down into smaller ones. So remember in your answer to always write that there's a catalyst involved because it's a chemical reaction. And remember the temperature, it's 500 degrees and the pressure is just above atmospheric. So that concludes today's discussion about the production of ethylene. We discussed, amongst other things, how to produce it by either, as we have here in my diagram, my very poor diagram, catalytic cracking using a zeolite as a catalyst, and there's also something called thermal or steam cracking. And the reason that we produce ethylene is because in petroleum there's very little ethene in there, and we have a very high demand for ethylene because we can make so many things out of it in the petrochemical industry. Now, next topic, we'll be talking about the things we can make by using ethylene. So that's today's topic, and next topic will be all about the uses of ethylene.